All right, let's get rolling. On the first page here, just like on the first page of our homeostasis lecture, is a figure that I'm going to refer to even before we start to lecture. It's a little cartoon, and probably at this point you're not going to really understand the cartoon, but it does kind of provide us with a theme that I want you guys to keep in your mind as we get to various points in this lecture. We probably won't get to that really too much at this point, but we'll get to it for sure on Monday. What we can see in this figure is a couple fellows inside of a classroom. Notice each of those fellows has a positive symbol attached to them. Those represent various what we call ions that have a positive charge. Outside of the room are some ladies, and you'll notice that there is kind of an attraction going on between those fellows. They're paying more attention to the ladies than they are at the teacher. Okay, those ladies all have a negative symbol attached to them. The kind of theme or motto that I want you guys to think of as we talk about this lecture, and I'll refer back to this figure, is a phrase that you hear in chemistry, but you also hear about it when people talk about their love lives. Opposites attract. So we'll talk about how opposites attract and why that's important throughout this lecture. We won't get to that, like I said, though, until probably Monday. Let's first of all just define chemistry, along with some other things. Okay, defining chemistry. This is the science of structure and interaction of what we call matter. So matter is important to understand because that's what we talk about in chemistry. Matter is anything that has mass and occupies space. So we see a new term probably, or maybe you've seen the word mass before. It's a term that you hear a lot of. We talk about a person's size. Mass, scientifically, is defined as the amount of matter in any object, and it does not change. Thank you to the law of conservation of matter. So mass, as I mentioned, a lot of times gets used when people talk about someone's size. Okay. Matter doesn't change. Weight is another thing that people use to describe someone's size. Is the force of gravity that acts on matter and will change. Okay, so mass is amount, weight is more related to gravity. It will change. For example, if you take your weight here on Earth, it's going to be different than it would be if you were on the moon. Okay, because there's a lot less gravitational pull on the moon than there is here on Earth. That's why astronauts float when they're in space. Okay. What will not change here or on the moon is the amount of mass an individual has, okay, or an object has. You can think of matter as far as really just about anything. Okay. I look around the room and I see your tables and your chairs. Gage is over there drinking water. Okay. Water inside of his big old cup there is a form of matter. It's a liquid form of matter. Okay. There are solid forms of matter. In the atmosphere right now, we can't see all the gases, but those are gaseous forms of matter. Water is a pretty amazing form of matter because it actually exists here on planet Earth in all three of those states or phases. It's a liquid as water in a drinking cup. It's a solid as ice, and it's all around us. And we actually breathe some of this out as a gas. Okay. So that's pretty amazing. Water, for that reason, is very essential to the human functionality. Okay. All forms of matter, both living and non-living, are made up of what we call atoms. An atom is defined as the smallest stable of unit matter. Atoms are extremely small. 200,000, the largest atoms would fit on the period of the end of this sentence, which is pretty amazing. Element is the type of matter that cannot be broken down into two or more pure substances. Matter composed of only one kind of atom. This is where that periodic table comes into play. And if you've taken biology, you would have learned about the periodic table. If you've taken chemistry, even at the high school level, probably even back in middle school, you've been exposed to the periodic table. There is a periodic table in your textbook, which you can refer to. It's in the back, not completely to the back, it's before the glossary, but it's back there. You can also Google them and find them. I'm sure you've all seen a periodic table before. Okay? The periodic table is more specifically known as the periodic table of elements. Each of the little boxes of a periodic table will have various information about those elements and what one atom of that element is structured as. How it's structured. Okay. Compounds are pure substances that contain more than one element, like water, which we know is going to contain two atoms of hydrogen, one atom of oxygen, which is why water is also known as H2O. There is an element, hydrogen, element, oxygen in water. And H2O is its chemical formula, and that is a fixed composition, meaning that it must be H2O to be water. It cannot be H3O, H2O2, anything like that. That's not water. That would be something else. Those things, H3O doesn't exist. Okay. That's what it has to be. C6H12O6 is the chemical formula for, anybody know?
What did you say?
C6H12O6? Glucose. 6 carbons, 12 hydrogens, 6 oxygens. There's 3 different elements and a whole bunch of different atoms of those elements. Speaking of that periodic table, I've included a very small excerpt of it. Top left of our page, which actually is the top left of the periodic table. We're showing off a few examples of those elements. Once again, the element is the simplest form of matter with unique chemical properties. The periodic table can be used to organize the basic information about those elements of the universe. Okay. On the periodic table, which is going to contain hundreds of little boxes, you're going to find a lot of information, and within those boxes you're going to find at least 3 things. Okay. Sometimes you'll find the name, sometimes you'll just find it with a singular capital letter or a capital letter and a lowercase letter. The abbreviation is what we're looking at here. Okay. Sometimes it's really easy, like H for hydrogen, Li for lithium. Sometimes it's a little trickier when you have like things like Na for sodium, Au for gold, K for potassium. Some of these you guys are going to just be able to rattle off by the end of the semester because we deal with them so much. Okay, most of them we don't. Okay, because there's not a whole lot of elements really that important to us in the human body. We're making this up. Okay. Above the abbreviation is a number, and below it is another number. The top number is the atomic number. The bottom number is the atomic mass. It might not be a bad idea if you can't remember that to write next to atomic number here. Top number next to atomic mass might not be a bad idea. Bottom number. Now, those numbers tell a lot of information about one atom of that element. Looking at hydrogen, the atomic number is 1. Well, what does that tell you? It tells you the number of protons in the nucleus of that singular atom of that given element. So for every atom of hydrogen, you're going to find 1 proton. We'll talk about what protons are here in a little bit. Okay. The bottom number is the atomic mass, and it is equal to the mass, obviously, hence the name, of that given element. And we calculate it as the number of protons plus the number of neutrons. So, from that we can calculate a lot of other stuff. Namely, not a lot of stuff, but namely we can calculate how many neutrons are in that atom. Let's use beryllium as an example. Okay, has atomic mass of 9.0122. We'll just round it back down to 9. Okay. We said that it has 4 protons because its atomic number is 4. Well, this number gives you protons plus neutrons. So doing very simple math, how many neutrons are in beryllium? 5. How did you learn that? Or how did you figure that out? 9 minus 4. That's as simple as it gets. Okay. How about lithium? We'll round up from 6.9 to 7. How many neutrons are in lithium? 4. Because 7 minus 3 gives you 4. Does that make sense?
But doesn't that say number of protons plus number of neutrons?
Yes. Sorry, I kind of flipped over to, I should just put it all on one slide or one line. What about hydrogen? Let's calculate hydrogen. We've got 1.0079 is its atomic mass. 1 is its atomic number. How many protons are in hydrogen? This tells you protons right here. 1. This number tells you protons plus neutrons. So, how many neutrons? Let's round this number to 1. What's 1 minus 1? 0. So hydrogen in this state has 0 neutrons. Does that make sense? Okay. As far as elements go, there are 26 different chemical elements normally present in one's body. Of those, only really 4 are majorly in the body. Oxygen, carbon, hydrogen, and nitrogen, they make up 96% of our body's mass. So by far and away, they're the most prevalent. I've always learned it as CHON, C-H-O-N. If you want to change that around, you could spell it notch or onch, whatever, to remember. Those are the majority of our body. They make up the big bulk of who we are. They also are responsible for making up the inside and everything of all living things. And all organisms are made up of those 4. Not completely, but almost. So predominantly. 8 others. The lesser elements make up about 3.8% of the body's mass. These include calcium, which we know is found in bones and teeth. So is phosphorus. Potassium, sodium, and chlorine, we'll talk a lot about those, especially potassium and sodium. Those are very, very important for nerve impulses, action potentials. Magnesium we don't talk too much about. We do talk a little bit about iron. It's important in our blood as a key component for hemoglobin. Without iron, we wouldn't be able to transport oxygen, and that's absolutely essential for life. And then there's an additional 14 trace elements. They're very, very small in amounts, just 0.2% of our body's mass. And they're not even listed in this table, 2.1. The table is from your textbook. I don't expect you to worry about knowing this table or anything like that. It's nice because it shows you those 4 majors and then the lessers. Gives you their abbreviation. It gives you their percent of total body mass, which is pretty cool. And then their significance. But that's not something I'm going to specifically ask you to know for the test. Let's get back and talk more about atoms. Okay, as we've already said today, a single atom of a given element is what's represented in the periodic table. And each one of those atoms is going to contain several different types of subatomic particles. We've already talked about protons and neutrons. Okay? These protons and neutrons give each element very unique chemical properties. Okay, along with protons and neutrons, we also have what are called electrons. Now, protons and neutrons are found within what we call the nucleus, the dense core of an atom. This is the center where the majority of the weight or mass, let's not use or, let's use mass instead of weight, the mass of an atom is located. Okay. We'll also see the term nucleus when we get to talking about cells. The nucleus in both cells and atoms is kind of the core of the structure. Okay. In cells, we'll talk more about what it is going to do. The nucleus in an atom contains the protons and the neutrons. Now, protons, which begin with the letter P, and I emphasize the letter P because they have a positive charge, okay, which the word positive also has the letter P. Okay. Neutrons are uncharged. Okay. I like the term neutral to describe neutrons because neutral and neutron sound very similar. Okay. Surrounding the nucleus in an atom are these electron shells. Sometimes you'll see them labeled as layers or rings. This is where you find electrons. Electrons which are negatively charged. So we've got positive stuff, we've got negative stuff, and we've got neutral stuff. Those are the three major subatomic particles in an atom. We can see a figure here on the next page to show off, a couple figures actually, to show off those subatomic particles in the structure of an atom. I'm not really a big fan of the electron cloud model. I like the electron shell model because it shows you those. Here you can even see the location for the number of electrons. Okay. Now, in a normal atom, like every single one of those you see in the periodic table, the number of electrons is going to be equal to the number of protons. So if we go back to our very small excerpt of the periodic table, the atomic number we said told you protons, right? Like 4 here for beryllium. Beryllium has 4 protons. And I just said that in a normal atom, these are all normal atoms, protons equal electrons. So atomic number not only tells you protons, it also tells you the number of electrons. So how many electrons are in hydrogen? How many electrons are in hydrogen?
Wouldn't it just be 1?
It would just be 1. This top number tells you protons, but the number of electrons is always equal to protons when we look at this. So this number also tells you the number of electrons. Now, the location of those electrons is going to be in these rings or layers or levels or shells, whatever you want to call them. Call them energy levels here. And each of those rings can only hold a certain number of electrons. The first ring will only hold 2. The second ring can hold up to 8. The third can hold up to 18. So on and so on and so forth. We don't really get into too many. Okay. We always fill the first towards the outer last. Okay. We always want the outer to be full, and we'll talk about that here in just a minute. I can tell you right away that this is showing off carbon. I know that because I know the atomic number of carbon. What would the atomic number be for this atom? 6. All you have to do is count electrons. 1, 2, 3, 4, 5, 6. Okay. The atomic number of carbon is 6. Okay. So you could go in here, you can't really see them all, but there will be 6 of those red dots to represent the number of protons. Okay. Carbon also actually has 6 neutrons, so it's got 6, 6, and 6. Okay. What this accomplishes by having the number of protons and the number of electrons equal is nice, creating an electrically neutral atom. So all those atoms that you see in the periodic table have no charge. Okay. They're neutral. Does that make sense? Now, are they going to stay that way? Not necessarily. Before we talk about changing charges, talk about isotopes. We can describe isotopes as just alternate forms of an element, meaning that there are sometimes multiple forms of the same element on Earth. What we mean is that they're going to have a different number of neutrons. For example, down here at the bottom, we see 3 different forms of hydrogen. The most common form of hydrogen is this one. Hydrogen 1, or what's called protium. If we go back to the figure where we saw that box for hydrogen, had atomic number 1, atomic mass 1, which told us it had 1 proton. How many neutrons? 0. How many electrons? 1. And what you see in the periodic table is going to be the most prominent form of that element. There are also 2 other forms of hydrogen. They're just not very common. And here is our hydrogen 1 proton, no neutrons, 1 electron. There's also deuterium, 1 proton. Now we have a neutron, 1 electron. What does that accomplish? Well, it creates a form of hydrogen that's going to have an atomic mass of what? It's not going to be just 1 anymore. It's 1 plus 1, which is 2. What's going to be the atomic mass of tritium? 3. Now you might be wondering, why don't we count electrons in with atomic mass? Why is it just protons and neutrons? Electrons, I think the book considers those to be like the size of a gnat compared to us. They don't exert much mass at all. So most of the mass comes from the stuff that's in the nucleus. Okay. Now, why is this important to us? Well, in health and medicine, we can talk about radioisotopes. Radioisotopes are described as very unstable isotopes because of what they do when they break down. Okay, they decay or break down, if you want to think of it real simply. And as they decay, they emit a lot of energy in the form of radiation, which you hear the word radiation, and most of the time you're going to think of that as a bad thing, right? UV radiation that we get from the sun and tanning beds can be detrimental to our health. You get radiation from a lot of different things. Hopefully not too much, because it can cause bad things to happen to you. Cancer is a very, very common result of getting too much radiation. And anybody ever heard of Chernobyl before? Chernobyl refers to a city, I believe it was in Ukraine, that had a nuclear power plant melt down. It was like 1990-ish, somewhere around there, probably before most of you guys were even thought of. Okay. That city has remained empty ever since because of the amount of radiation that's being still emitted. Okay. Nobody's going to be allowed there without government approval and without like a hazmat style suit for a very, very, very long time. And the people that live there were told, I think, like, you will be back in 2 weeks. So they just picked up what they needed, and now they're still not able to get back. Okay. The fish that they catch in like streams and rivers downstream from there are going to be a lot of mutated, nasty, whatnot. And there's an episode of River Monsters where the main character gets to go and fish there, and it's pretty wild what he pulls out of the ponds and stuff around there. So anyway, that's a very extreme case of radiation. Okay. Some radioisotopes actually are very helpful for health and medicine. They can be used as what we call tracers. It allows them to follow the movement of certain substances in our body to detect certain diseases in the body, like what we see here on the right. Okay. The last one, thallium-201, I believe, is the one that they inject into a person's bloodstream and then have them perform a stress test. Where a stress test is where they hook them up to an EKG, have them run on a treadmill and see how the heart does. What the thallium-201 allows for is to detect blockages in the coronary arteries so they can see if somebody's at risk for a heart attack, diagnose them as having heart disease. Now, thallium-201, I believe in the book, it talks about the fact that its half-life, which is the stuff that's talked about there in that first bullet, where it basically is just removed, decays into a stable form, is just a couple of days. Some, and those like what happened with Chernobyl, that half-life of that radioisotope is hundreds, even thousands of years. So it can be very dangerous. And that's why nobody can go within so close to Chernobyl. All right, back to molecules and compounds. We already defined compound once today, but it's okay, we'll define it again. A lot of times you'll hear me use these two terms synonymously, and I will use them interchangeably. Technically, they're not. To be classified as a molecule, it has to be with the sharing of electrons. Whereas compounds, they don't necessarily share. I'll explain that here in a minute. Molecular formula indicates the elements and the number of atoms of each element that make up a molecule. So we have O2. We all know O2 is what? Oxygen gas that we breathe, right? This tells you, O here, the element involved is oxygen. The sub 2 here tells you that it has 2 atoms of that. So it would be 2 atoms of oxygen to form oxygen gas. Now, that's an example where it's the same element. There can also be different kinds of atoms or different kinds of elements. Like H2O, which we said already is water, 2 atoms of hydrogen. Now, if it doesn't have a number after it, you can assume it just means 1. So there's 1 oxygen atom. C6H12O6, I said earlier, is chemical formula for glucose. 6 atoms carbon, 12 hydrogen, 6 oxygen. Okay. Those are considered to be molecules because they're sharing electrons. Compounds don't necessarily share electrons. Okay. A compound is defined as a substance containing atoms of 2 or more different elements. Okay. Like in the case of water, which we just talked about, which can be classified as a molecule or a compound. Okay. Sodium chloride, NaCl, the atoms are not sharing electrons here. So sodium chloride cannot technically be called a molecule, it can only be called a compound. Now, like I said, I'll probably use those terms kind of interchangeably, but just know that's not technically correct. Most of the atoms in our body are joined into compounds. Anybody know what sodium chloride is best known as? Salt, table salt, absolutely. Now, before we get into forming molecules and compounds and learning how and why, I want to talk just briefly about free radicals, which are electrically charged atoms or group of atoms with an unpaired electron in the outermost shell. When you have an extra electron, you have an extra negative charge, which makes a free radical very unstable, highly reactive, and destructive to nearby molecules. I kind of think of this like the Tasmanian devil. Everybody know who he is from cartoons? What's he do? He comes in, he spins around, and he destroys everything in his path. Or tornado. Okay? Bullet and china cover. These are all kind of the same synonyms to describe, not synonym, something that screws everything else up. Okay? What free radicals are known for causing in our body are things like cancer. They can lead to Alzheimer's disease and other stuff that's not good for us. Okay? What we want is for those free radicals to become stable again by either giving up that unpaired electron to or taking an electron from another molecule. This may lead, though, to the breakup of bonding molecule. Like what we see here with oxygen when it gains this extra electron becoming a superoxide free radical. Anybody ever heard of antioxidants before? Okay, you get antioxidants in a lot of fruits and vegetables. If you get a good balanced diet with fruits and vegetables, you're getting a lot of antioxidants. Green tea, you'll see a lot of times on a bottle of green tea, great source of free radicals. Not free radicals, antioxidants. Antioxidants help neutralize free radicals. So get your antioxidants. All right, I think we'll pick up with chemical bonding. It'll be a perfect spot to start on Monday.